top of the world, where winter swallows the sun for months at a time, a predator once ruled. Not in a jungle, not in a desert, but in a land of darkness, cold, and long silence. It looked like a T.rex, but it wasn't. It was something stranger, an apex hunter built for a world that should have been impossible for dinosaurs to survive. And for millions of years it did. Around 68 million years ago, in the late Cretaceous, North America was a continent of contrasts. To the south, broad floodplains and forested lowlands supported a rich and familiar ecosystem, home to giants like Tyrannosaurus rex. But far to the north, the landscape changed. In what is now northern Alaska, the Prince Creek Formation preserves evidence of a very different environment. This was not an ice-covered wilderness, but a cool, seasonal polar region, with forests, rivers, and long periods of darkness in winter. Conditions were harsher, resources less predictable, and survival more demanding. The Arctic was not empty. It was a different kind of world, one that required a different kind of predator. In 2006, a field team working in the remote outcrops of the Prince Creek Formation uncovered a set of fragmentary theropod remains, parts of the skull, including a right maxilla, elements of the skull roof, and additional cranial material. At first glance, there was nothing obviously unusual about them. The shape and proportions closely resembled known tyrannosaurs from lower latitudes. The initial assumption was straightforward. These fossils likely belonged to a familiar genus, perhaps a northern occurrence of species related to Albertosaurus or Gorgosaurus. If so, the discovery would still be important, extending the known range of large tyrannosaurs much farther north than previously confirmed. But as preparation continued and the material was studied in greater detail, subtle differences began to emerge. The structure of the skull, particularly features of the frontal and parietal bones, did not fully match any known tyrannosaur. These were not just variations within a species, they pointed to something distinct. The conclusion became increasingly clear. This was not a known animal. It represented a new genus, formally described in 2014 and named Nanooksaurus, meaning polar bear lizard. The name reflects more than geography. It captures a fundamental shift in understanding. This was not a transient predator passing through the Arctic. It was adapted to it. Not a visitor, but a resident. Once identified, the next question was placement. Where does Nanooksaurus fit within the Tyrannosaur family? At first glance, its anatomy is unmistakably tyrannosaurine. The skull is deep and powerfully built. The neck forms the familiar S-curve, and the overall proportions suggest an animal designed for force rather than speed. In this respect, it shows clear similarities to relatives such as Albertosaurus and Gorgosaurus. Both well-known predators from southern regions of late Cretaceous North America. Detailed comparisons of the skull, however, reveal that these similarities are not exact. Certain cranial features, particularly the structure of the frontal bones and the pronounced ridges above the eyes, distinguish it from previously described genera. These differences are subtle but consistent, showing this was not just a northern population of a known species. It represents a distinct branch of Tyrannosauridae, closely related to Tyrannosaurus rex but not the same animal. Its evolutionary origin remains unresolved. One possibility is that it descended from North American tyrannosaurs that gradually expanded their range northward, adapting over time to increasingly seasonal conditions. Another point is across the ancient Bering Land Bridge, which intermittently connected Asia and North America during the late Cretaceous. In this scenario, ancestors from Asia dispersed into the Arctic and remained there, isolated from populations farther south. Both explanations are plausible, and neither is yet conclusive. What they share is, these predators were not confined to a single region. Estimating the size of Nanooksaurus has been one of the most debated aspects of its biology, largely because the fossil record is so limited. The original material consists mainly of partial skull elements, including a maxilla and fragments of the skull roof. There is no complete skeleton and no associated limb material. From the beginning, any size estimate has had to rely on comparison rather than direct measurement. Early estimates based on the proportions of these skull fragments suggested a relatively modest animal for a tyrannosaur, around 16 to 20 feet in length, weighing close to 1,100 to 2,000 pounds. By those measures, it would have been smaller than many of its southern relatives, more comparable to mid-sized members of the group. However, later studies introduced a different possibility. By comparing the available skull material with growth patterns seen in other tyrannosaurs, some researchers have proposed that the known specimen may represent a juvenile or subadult. If that is the case, then the original estimates are likely too low. A fully grown Nanooksaurus could have reached closer to 8 or 9 meters in length, with a mass approaching 2 to 3 tons, bringing it much nearer to animals like Albertosaurus. The difference between these estimates is significant. It changes not only how large the animal was, but how it may have functioned within its ecosystem. Yet the uncertainty remains. No complete skeleton has been found, and no fully mature individual has been definitively identified. To understand Nanooksaurus, we have to shift focus from the animal itself to the environment that shaped it. Because in the Arctic of the late Cretaceous, survival was not defined by strength alone, but by endurance. This was not the frozen polar desert we know today. Fossils from the Prince Creek Formation show a landscape of river channels, floodplains, and forests. Yet despite this productivity, conditions were far from stable. Temperatures during winter likely dropped to around 26 degrees Fahrenheit, cold enough to freeze water at the surface. Snowfall and seasonal storms would have been common. But the most defining feature was not the cold, it was the darkness. For up to 120 days each year, the sun remained low or absent entirely. For a large predator, this presents a fundamental challenge. How does a hunter operate when visibility is limited for months at a time? One possibility is insulation. While no direct fossil evidence confirms it, Tyrannosaurus may have been feathered, at least partially. This idea is supported indirectly by related theropods such as Tyrannosaurus, which lived in cooler climates and possessed extensive feather covering. If similar features were present here, they would have helped retain heat during prolonged cold periods. Its senses may also have been critical. The structure of the nasal region suggests that its sense of smell may have been highly developed, possibly even more pronounced than in Tyrannosaurus rex. In low-light conditions, the ability to detect prey by scent over long distances would have been a major advantage. Vision, too, may have been adapted for dim environments, allowing it to track movement in twilight or near darkness. None of these adaptations can be confirmed with certainty. They remain informed hypotheses, grounded in comparison rather than direct evidence. But together, they point to a consistent conclusion. This was not an environment that tolerated weakness, and any predator that lived here was shaped by it. In the Arctic, hunting was shaped by constraint, by darkness, distance, and uncertainty. For Tyrannosaurus, the challenge was not simply overpowering prey, but locating it in a landscape where visibility could disappear for months at a time. The fossil record from the Prince Creek Formation shows that large herbivores were present, including Edmontosaurus and Pachyrhinosaurus. These animals were not only large, often weighing several tons, but also likely moved across broad ranges, influenced by seasonal changes in food availability. This meant encounters may have been infrequent, especially during the long winter months. Under these conditions, high-speed pursuit would not always be reliable. Snow, uneven ground, and low light reduced the effectiveness of chasing strategies. Instead, hunting likely began with detection. A well-developed sense of smell may have allowed Tyrannosaurus to locate carcasses or live prey over distance. Subtle sounds or movement in dim light may have provided additional guidance. Once within range, however, the strategy would shift. Like other tyrannosaurs, it possessed a large, heavily built skull and strong jaws. While exact bite force remains unmeasured, comparisons with relatives suggest the capacity to deliver a single, decisive bite, one capable of crushing bone and inflicting severe trauma. In this context, accuracy mattered more than endurance. One opportunity, properly executed, could be enough. Modern reconstructions often depict multiple individuals coordinating attacks on large prey, especially animals like Pachyrhinosaurus. It is a compelling scenario, particularly in a harsh environment where cooperation might seem advantageous. But this remains speculative, often imagined, but not supported by direct evidence. There is currently no clear fossil evidence that Tyrannosaurus hunted in organized packs. What the available evidence suggests instead is a capable, solitary predator, one that relied on its senses, timing, and strength to survive in a world where opportunities to hunt were limited. One of the most striking patterns in the fossil record of Dinosaurus is the age distribution of the individuals we find. Across specimens recovered, a large proportion appear to belong to juveniles or subadults. Fully mature individuals, by contrast, are rare and in some cases absent from the current record. This imbalance is not random. It points to a harsh biological reality. In this Arctic environment, survival rates were likely low, especially during early life stages. Young individuals would have faced multiple pressures at once: limited food availability, extreme seasonality, prolonged winter darkness, and the constant risk of injury or starvation. Even reaching adulthood would have required navigating years of uncertainty. What makes this pattern particularly revealing is that it appears in a top predator. Dinosaurus was not a vulnerable species in the traditional sense. And yet, the environment itself imposed limits that even apex predators could not fully overcome. There is also another implication. The high number of younger individuals suggests that these animals were not migrating south during winter, but remaining in the Arctic year-round. If true, this would mean that entire life cycles, from birth to adulthood, took place under these extreme conditions. It is a reminder that dominance does not guarantee survival. Even apex predators struggle when the environment turns against them. In the end, Dinosaurus is not simply a northern version of Tyrannosaurus rex. It represents a distinct response to a very different environment, one shaped by seasonal darkness, colder temperatures, and limited resources. Its anatomy, distribution, and fossil context all point to a predator that did not just pass through the Arctic, but lived and adapted there over time. The late Cretaceous Arctic was not empty. It was a dynamic system where survival required flexibility, endurance, and constant adjustment. In that setting, Dinosaurus stands as evidence that even large apex predators could expand beyond what we once considered their limits. The Arctic did not belong to the weak, and for a brief moment in deep time, it belonged to a tyrant. If you value careful, evidence-based storytelling like this, subscribe and supporting our channel for more.